implementing spanning tree protocols, topology, DLS1 and DLS2, layer 3 switches, and ALS1 and ALS2 layer 2 switches, host A, PC, okay, between DLS1 and DLS2, fast Ethernet 11 and fast Ethernet 12 on both sides. Okay, add interfaces. I need 7 interfaces. Okay. Okay, between DLS1 and DLS2, fast Ethernet 11 and fast Ethernet 12. In my case, use the connect tool. I will connect 1, 1 and 1, 2, 1, 1 and 1, 2. In this side, between DLS1 and ALS1, 7 and 8, I will use gigabit 01 and gigabit 02. The another side, the same way. Between DLS1 and ALS2, 9 and 10, and between DLS2 and ALS1, 9 and 10. I will choose 03 and 10. 03 and 10. Okay, and a PC on fast Ethernet 6 on ALS1. Okay, in this case, LXC Linux container connected to, in this case, gigabit 13. Okay, if you want to use this Linux container LXC, it's necessary to build initial configurations to create the username and password on this and this Linux container. If you will not use this, it's not necessary to build initial configurations. Okay, I will do it. No. Okay, ready and launch simulation. Yes. Okay, all devices in green. Observe default spanning tree behavior. Load base config and configure trunks. Okay, use the reset TCL script you created in lab 1, preparing the switch to set your switches up for this lab. Then load the file base.cfg into the running config with the command copy flash base cfg to running config. Okay, run the script and copy the file. Okay, this is the script for base.cfg, or you can use these commands to copy and paste to the device. All this for the basic configuration. Okay, and for a layer 3 switch, you can use this script to delete the VLAN file, the multiple FS file, and set the SDN preferred. Okay, or you can use these commands. Also, for layer 2 switch, you can run this script to delete the files or use these commands. Okay, for example, verify DLS1 console port, enter, enable. When you run build initial configurations, the password is Cisco, and you can show running configurations. Okay, for example, you have a gigabit 00, 1, 2, and already configured. Okay. Good. Okay. Okay, and also the okay, for example, show flash. Okay, dir. Okay, all the switches will have initial configurations. Okay. Okay, for example, for a layer 3 switch, use these commands, but this command is created for a layer 3 switch on a real lab, 3560 switch. So on BIRL or GNS3, you can only apply, for example, this. There's another line, these 2 lines, but this is not supported. The SDN prefer and then reload. Okay, okay, and remove this. And use only these commands. Okay. User accept modes. Okay. And we'll reload the device. DNS2. Enable Cisco. ALS1. Enable Cisco. ALS2. Enter. Enable Cisco. Okay, okay, remember that this blank line is an enter key. Okay, to confirm using the enter key, confirm and confirm after reload command. Okay, a blank line. Okay, DLS1 enter. Okay, this is the host name by default. That means you erased all contents successfully. Okay, now apply the basic settings. The basic settings up here. This is the script, but you can use these commands. Okay, and shut down all interfaces gigabit 01 to 03, gigabit 10 to 13. Okay, and gigabit, there is a gigabit 00. I'm not using that, but I will shut down that interface anyway. Gigabit 00, gigabit 01 to 03, and gigabit 10 to 13. All the interfaces shut down. BTP mode transparent, and line console now exit timeout and login synchronous. Very useful. Okay. Apply these basic settings on all devices. Enable configure terminal. Okay. Hostname DLS1. Enable configure terminal. DLS2. ALS2. Okay, for example, verify DLS1 and show running config. Show running config. Okay, the interfaces with no configurations. Okay, that is very good. You can start from 7 to 12. Configure strong ports. Okay, configure this on all switches. Okay, this was previously configured on previous labs. Okay, I will copy and paste this from 7 to 12. In my case, is from the trunk ports from 01 to 03 and 10 to 12. 13 is not in use. Okay. The trunking ports are 6 interfaces, 01 to 03 and 10 to 12. Okay, from 01 to 03 and 10 to 12. Okay, only the trunking ports, only 6 interfaces. Okay. Apply in all devices. The encapsulation .1q, then a VLAN 666, allowed all VLANs except 1 and 999, set the mode trunk and non-negotiate to disable dynamic trunking protocol. DLS1 configure terminal. DLS2, ALS1, and LAS2. Okay, configure all 4 switches as BTP version 3 servers in domain switch lab with no password. Okay, these 3 commands on all switches, okay, as configured in previous labs, do not use a password. So you need to remove the password and use only these 3 lines. Okay, configure belongs. DLS1 BTP primary server for belongs. Okay, and create all the belongs, all these belongs, only on DLS1. Okay, only on DLS1. That is the BTP primary belongs for BTP version 3. Okay, go to DLS1, exit, user exit mode, BTP primary belong. Okay, this system is becoming primary server for feature belong. Okay, wait some seconds and confirm, press enter. Yes. Create the belongs, configure terminal, belong 99, name management, belong 100, name servers, guest 120, office 999, parking lot, state for this suspended, .666, the native. And exit to apply changes for the belongs. And verify the BTP status for DLS1. Show BTP status. Okay, version 3, domain name. This is the primary server, and this is the ID for this primary server. That match with the ID, the device's ID. Okay. For example, on LAS2 and verify show BTP status. Okay, version 3, switch lab, only server, no primary, and this is the ID for DLS1, and this is the ID for local device. Okay, very good. Show VLAN brief. Okay, all belongs. All belongs. Okay, obtain it from DLS1. Identify and modify the root bridge. Show spanning tree root command on all the switches to find the root switch. For all the belongs. Okay, DLS1 show spanning tree root. Okay, apply this command and all the switches and paste, enter, and paste, enter, paste, enter. Okay, for example, on DLS1, okay, these are the belongs. Okay, but look at this. This belong is not part of this activity, so verify DLS1, show belong brief. Okay, remove this on DLS1, configure terminal, now belong number 2. Okay, and show belong brief. Okay, now very good. The one is by default created, cannot be removed, and all the belongs that I just created. Verify on LAS2, show belong brief. Okay, this is very good. Okay, DLS2, show belong brief, very good. And okay, continue. Use the show spanning root command on all switches to find the root switch for all the belongs. Okay, your results may vary from the examples. Okay, in all the switches, use that command. DLS1 show spanning tree root. Okay, in all devices, enter. ALS1, ALS2. Okay, very good. These are the belongs, the active belongs. Remember that belong 999 is suspended. Okay. This is the root ID. Okay, the base MAC address for the root switch. And this is the root port, gigabit 03. Okay, this is the port that you can reach the root, gigabit 03, and you can see on ALS2, gigabit 03 is facing the DLS1. So DLS1 can be the root switch. For all belongs gigabit 03 using this cost 4. Okay, remember that I'm using gigabit interface. For example, on ALS1, these are all the belongs. This is the root ID for the base MAC address of the root switch, and this is the cost using gigabit 01. ALS2 gigabit 01 is facing DLS1. So DLS1 can be the root switch. Okay. Finally, DLS2 gigabit 11. Okay, that also is facing DLS1. Okay, that means that DLS1 is the root bridge. Okay, click on DLS1. Okay, on DLS1, no root ports. That means that you are the DLS1 is the root bridge or root switch. No cost. Okay, so that confirms that DLS1 is the root bridge. Okay, also apply the show spanning tree belong 99 to verify the root for this belong. Okay, DLS2, for example, DLS2 show spanning tree belong 99. Okay, for belong 99, the root ID. Okay, for the root bridge, the priority 32,867. The address for the root bridge is this, DLS1. The cost for using the port gigabit 11. Okay, 11 facing to DLS1. The local DLS2 ID priority this. Okay, remember 32,867 is the result of the priority by default 32,768 plus the belong 99, the system ID. Okay, the local base MAC address. Okay, basically the MAC address of the root bridge. Okay, basically DLS1 has the lower MAC address than the other switches in the belong. Okay, all this port in forwarding state. But look at this, 11 is a root port that is facing DLS1, the root bridge. Okay, that's why it's a root port. And the another ports are designated ports. Okay, so the state is forwarding. And the alternative port is blocking state. The current root bridge was elected based on the lowest bridge ID consisting of the priority extended system ID equal to the belong ID and base MAC address values. In the output above, the root MAC is the base MAC address of the device. The local bridge is a higher value, a higher base MAC address. With the priority and extended system ID being identical, the root bridge MAC is numerically smaller than the local bridge's MAC. The end result is that in a completely unconfigured network, one single switch will be elected as the root bridge. The resulting choice of switch may or may not be desirable. There are two basic ways to manipulate the configuration to control the location of the root bridge. The spanning tree belong ID priority and value command can be used to manually set the priority value. The spanning tree belong ID root primary or secondary command can be used automatically set a priority value. The difference between the two, the priority command will set a specific number, multiple, or 4096 as the priority, while root primary command will set the local bridge's priority to 24,576 if the local bridge MAC is lower than the current root bridge's MAC, or 4,096 lower than the current root's priority if the local bridge MAC is higher than the current root's bridge's MAC. The logic behind this operation is straightforward. The root primary command tries to lower the priority only as much as is needed to win the root election, while leaving priorities between 24,576 and the default 32,768 for use by secondary bridges. The command always takes the entire bridge ID into account when computing the resulting priority value. The spanning tree VLAN ID root secondary command will statically set the local bridge's priority to 28,672. In an otherwise unconfigured network where all switches' priorities default to 32,768, the root primary command will set the priority on the switch to 24,576, 2 steps lower than the default priority, while the root secondary command will set up the priority on the secondary root to the 28,672, 1 step lower than the default priority. Modify DLS1 and DLS2 so that DLS1 is selected the primary root bridge for VLANs 99 and 100, and DLS2 is selected the primary root bridge for VLAN 110 and 120. DLS1 should be elected as secondary root bridge for 110 and 120, and DLS2 should be elected as secondary root bridge for VLANs 99 and 100. Okay, for example, on DLS1, use these commands. DLS1 configure terminal spanning tree VLAN for 99 and 100 the root primary, and for 110 and 120 root secondary. DLS2 configure terminal VLAN and spanning tree VLAN 110 and 120 root primary. Okay, but for VLAN 99 and 100 root secondary. Verify, for example, on DLS1 and show spanning tree root. Okay, and now DLS2 is the root for 99 and 100 because the cost is 0 and not root ports. Okay, but for VLAN 110 and 120, the root ID is a different value, the ID of DLS2, and the root port to reach the root bridge is gigabit 11. Okay, on DLS1, gigabit 11 is facing DLS2. Okay, and DLS2 verified and show spanning 3 root. Okay, for 110 and 120, DLS2 is the root bridge, cost 0 and not root ports, but for 99 and 100, this is the root ID for DLS1, and the root port is gigabit 11 that is facing DLS1. Okay, on DLS1 also you can perform show spanning tree VLAN 99. Okay, I am the root bridge. The root ID match with the local bridge ID. Okay, but for VLAN 110, okay, the root ID is for DLS2 and the local bridge ID do not match with the root ID. Okay, to reach the root bridge DLS2, I will use the local interface gigabit 11. Okay, DLS1 gigabit 11. Okay, so that's why for VLAN 110, the root interface is gigabit 11, the interface that is facing DLS2. Okay, all interfaces designated interfaces, and gigabit 12 are the alternative blocking state. Okay, on DLS1 you can also perform this option, show spanning tree bridge, mark question to see the options. Okay, you can see the MAC address, the detail, the ID, the priority, and protocol, and other options. Okay, but simply just show spanning tree bridge, enter. Okay, you can see the VLAN. Okay, the bridge ID, the priority, the extended system ID, that is the VLAN, the number of VLAN, and the base MAC address. Okay, the priority plus the extended system ID is the bridge ID. Okay, the protocol is IEEE. Okay, all these values for the local bridge, for the local switch. Okay. Okay, remember that for VLAN 99 and 100, DLS1 is the root primary. The root primary set the priority to this value, 24,576. And remember that DLS1 is the root secondary for VLAN 110 and 120. And when you set the root secondary, you set the priority to 28,672. Okay. And finally, this another VLAN, the 666, uses the default priority plus the number of the VLAN, the extended system ID will result this bridge ID. Okay. Manipulate port and path costs. As network is implemented right now, there are two paths between each directly connected switch. As the root port is elected, path and port costs are evaluated to determine the shortest path to the root bridge. In the case where there are multiple equal cost paths, the root bridge Additional attributes must be evaluated. In our case, the lower interface number, for example 11, is chosen as the root port, and the higher interface number, for example 12, is put into a spanning tree blocking state. You can see which ports are blocked with the show spanning tree VLAN ID command or the show spanning tree blocked ports command. For now, examine VLAN 110 on DLS1. Show spanning tree VLAN 110. Okay, DLS1 is the root secondary and DLS2 is the root primary. Okay, and look at this. There are two ports that are facing DLS2. Okay, both have the same cost, number 4. Okay, but the priority and number for gigabit 11 is 28.6, and the priority and number for gigabit 12 is 128.7. So the lower priority number or the lower number interface is elected as the root, and the other interface as an alternate interface in blocking state. Okay, spanning tree blocked ports. Okay, for VLAN 100 and 110 and 120 gigabit 12. Two blocked ports. As you can see, VLAN 110 has its root port on fast Ethernet 11 and 12 is an alternate blocking port. It is possible to manipulate which port becomes the root port on non-root bridges by manipulating the port cost value or by changing the port priority value. Remember that this change could have an impact on downstream switches as well. Okay, and do not make these changes in a production network without careful planning and prior coordination. The first change you will make will influence the root port election based on a change the port cost. Okay, on DLS1, configure terminal interface gigabit and for example 9 and 10. In my case they are gigabit 03 and 10. Okay, interface range gigabit 03 and gigabit 10. Shut down. Okay, exit. Okay, on ALS1, verify the enter show spanning tree root. Okay, look at the difference before and after. Before, VLAN 110 uses ALS1 uses gigabit 01 to reach the root bridge, but now on VLAN 110 to reach the root bridge is using gigabit 03. Okay, so ALS1 will reach DLS1 for we'll use gigabit 03 to reach the root bridge. The election of the root port is based on the lowest total path cost of the root bridge. The root path cost is the sum of all of the root port costs between the local bridge and the root bridge. If the total path cost to the root bridge is the same over multiple ports, then the port towards the neighbor switch that has the lowest bridge ID is chosen as the root port. If the local bridge has multiple connections to a neighbor bridge that is in the lowest cost path, Bpdu sent from that neighbor are examined and the Bpdu containing the lowest sending port ID is chosen as the root port. In this case, the term sending refers to the switch and its port that forwarded the Bpdu. Okay, on ALS2, okay, ALS1 on VLAN 110 uses gigabit 03 to reach the root primary bridge DLS2. Okay, remember that DLS2 is the root primary for VLAN 110. Okay, it's directly connected. Okay, go to ALS2, enter, verify show spanning tree route. Okay, to reach VLAN 110 uses gigabit 01 to connect the DLS2, the root primary. Okay, the cost is 4. In this case, the cost is 4. For example, you can change the cost on gigabit 01. Okay, a lower value than 4. Configure terminal interface gigabit 01 spanning tree cost. Okay, I will choose 1, exit and verify show spanning tree route. Okay, the cost is 1 to reach the primary route DLS2 for VLAN 110. Look at the state on LAS1, enter, show spanning tree route again. Okay, the same state as before. Use this command, show spanning tree VLAN 110, and look at gigabit 11 with the cost 4 equal than the other interfaces. And also you can change this cost to 1, okay, to prefer this interface to reach the root primary for VLAN 110 DLS2. Configure terminal interface gigabit 11 spanning tree cost 1. Okay, G exit and show spanning tree again. Now this will be the root, so it's preferred. Okay, and verify this another command, show spanning tree root. So to reach the root primary for VLAN 110, that is DLS2, uses gigabit 11, okay, and the cost is 2. Remember, the cost on gigabit 11 is 1. Okay. Okay. Remember, the cost on gigabit 11 now is 1, and the cost on gigabit 01 on ALS2 was configured to 1. 1 plus 1 is the total cost of 2. Okay. On ALS1, previously, using gigabit 03 to reach DLS2, the root primary of VLAN 110, the cost was 4. If the cost is 4, set gigabit 11 to cost 1 and set gigabit 01 to cost 1, is a total cost of 2 and is preferred than 4. So that's why the root interface is now gigabit 11 and is preferred to reach the root primary for gigabit for VLAN 110 with the cost of 2. On DLS1, show spanning tree VLAN 100, DLS1, enter, and show spanning tree VLAN 100. Okay, the priorities, for example, by default 128 in all interfaces. Okay, focus on an interface. Notice that its port ID is made up of 2 values, labeled as priority and number. The priority by default 128 and the port number can be another number. The port number is not necessarily equal to the interface ID. On the 3560 used for creating this lab, port numbers 1 and 2 are assigned to gigabit 1 and 2 respectively, whereas 2960 gigabit 01 and 02 assigned the port numbers 25 and 26. The priority can be any value between 0 and 240 and increments of 16. Examine ALS1 to find the root port for VLAN 100. ALS1, show spanning tree root. Okay, for VLAN 100 uses gigabit 01. Okay, gigabit 01 that is facing DLS1. Okay, this is very good because the root primary for VLAN 100 is DLS1. Okay, so this is the root port and the cost 4. Okay, so gigabit 01 is elected because it has a lower value than gigabit 02. Okay, you can verify this using show spanning tree VLAN 100. Okay, in gigabit 01 and 02, gigabit 01 and 02 have the same priority, but the number of gigabit 01 is 2, a lower value than gigabit 02. Okay, so that's why gigabit 01 is preferred, is the root. Okay, but on DLS1, change the priority of gigabit 02. Okay, go to DLS1, configure terminal, interface gigabit 02, and you can set the spanning tree root priority to 112. Spanning tree port priority to 112. Okay, port priority in increments or 32 is required. Okay, this is required for BIRL, but on a real switch is the increments of 16. Okay, the default is 128 minus 32 is 96. So use 96. Okay, remember on DLS1 gigabit 02 in my case, and exit. And now go back to ALS1 and verify. Show spanning tree root. Okay, now the root is gigabit 02. The cost is the same, but the priority has changed on the other side. Show spanning tree VLAN 100. The priority, okay, gigabit 02 now is the root. Before the root was gigabit 01, but now gigabit 02 is the root, and the cost is equal, the same. The priority and number are equal because the changes were made in the another side on DLS1. Verify DLS1, show spanning tree VLAN 100, and you can see the change of the priority. Examine reconvergence time. Use the debug spanning tree events command on DLS1 and watch how long reconvergence takes when interface 11 on DLS1 is shut down. Faceted Net 11 is DLS1's root port for VLAN 102. Okay, first of all, on DLS1, use the following command. Okay, DLS1 debug spanning tree events. Enter. Okay, and shut down interface Ethernet 11. In my case, 11. Okay, configure terminal, interface gigabit 11, shut down. Okay, look at the events. Okay, remember DLS1 is the root primary for VLAN 99 and 100. VLAN 99 were spanning tree root. VLAN 100 we are the spanning tree root. Okay, VLAN 110 gigabit 12 listening. New root port gigabit 12 code 4. Cost 4. Okay. Okay, now gigabit VLAN 110 gigabit 12 learning and generating TC trap for port gigabit 12. Okay, Now VLAN 110 gigabit 1.2 forwarding. Okay, on DLS1, verify show spanning tree VLAN 110 gigabit 1.2 the root. Okay, remember that for VLAN 110 the root primary is DLS2. Okay, reestablish the interface. Configure terminal. Gigabit 1.1 no shutdown. Okay, Gigabit 1.1 listening. Gigabit 1.1 new root. Gigabit 1.1 new root port for VLAN 110. Gigabit 1.2 VLAN 110 blocking. Gigabit 1.1 learning. And generate TCP trap for port Gigabit 1.1. And verify show spanning tree (110). Okay, the root port now is Gigabit 1.1. Show spanning tree. Okay, and implement rapid spanning tree. By default, Cisco switches are running per VLAN spanning tree, which is a Cisco proprietary protocol derived from the AAA AF2.1d standard. Show spanning tree detail. Okay, on DLS1, for example, show spanning tree detail. Okay, for example, VLAN 99 is executing the AAA compatible spanning tree protocol. Okay, run this command, show running config. And the spanning tree mode is per VLAN spanning tree. Okay. Configure rapid. The issue with per VLAN spanning tree is that its convergence is quite slow. The time for the transition between port states is called forward delay, and by default it's 15 seconds. In addition, the time until Bpdu stored on a port expires is called max age and is 20 seconds by default. Depending on the nature of topological change, STP requires between 30 and 50 seconds to converge on a new loop-free topology. Rapid spanning tree significantly reduces the time it takes to go from the discarding per VLAN spanning tree blocking to the forwarding state. Okay, configure rapid spanning tree protocol on DLS1. Use the clear spanning tree detected protocols privilege X command to flash any stored per VLAN spanning tree information. Okay, use these commands on DLS1. Configure terminal spanning tree mode rapid spanning per VLAN spanning tree. Okay, and okay, the debug is activated. Okay, enter. Okay, disable this. Use the undebug all command. Okay, undebug all. Okay, ready. Okay, spanning tree, rapid per spanning tree was configured, and now clear spanning tree detected protocols. Now verify. For example, show spanning tree belong 120. Okay, rapid spanning tree. And now look at this. The type is peer STP. Peer STP. Now not only peer-to-peer. Okay, now peer STP. Okay, take a note of the type field in the output. All the other switches are still running per VLAN spanning tree, which is noted here by the entry peer STP. Okay, the peer is only STP, no rapid spanning tree protocol, only STP. Okay, configure the rest of the switches. Okay, DLS2, configure terminal, spanning tree mode, rapid per VLAN spanning tree. Enter. Configure terminal, rapid per VLAN spanning tree. Enter. Configure terminal, rapid per VLAN spanning tree. And finally, clear spanning tree detected protocols. Okay. And and to examine the impact of rapid spanning tree on convergence time, use the debug spanning tree event commands. Use the debug spanning tree events on DLS1 and watch how long reconvergence takes when interface fast Ethernet 11 on DLS1 is shut down. DLS1, enter. Debug spanning tree events, configure terminal, gigabit 11 in my case, shut down, okay, is very fast. Okay, verify and show spanning tree VLAN 120, for example. Okay, and establish the interface gigabit 11, no shutdown. Okay, that's all. It's very good, very fast. Implement STP tool kit components. In both STP and Rapid STP, a new connected port must be guaranteed not to create a switching loop before it can become a forwarding port. This may take up to 30 seconds. However, such a check is not necessary for ports connected to end devices that do not perform switching or bridging, such as workstation, network, printers, servers, etc. In Rapid STP, these ports are called edge ports. Ports that connect to other switches in the topology are called non-edge ports. Edge ports can safely enter the forwarding state right after they come up because by definition they do not connect to any device capable of forwarding frames. Cisco developed a feature called PortFast that essentially allows defining a port as an edge port. Any PortFast enabled port will enter the forwarding state immediately after coming up, without going through the intermediary non-forwarding states, saving 30 seconds each time a new connection is made to the port. PortFast can be used with all STP versions. Apart from allowing a port to jump into the forwarding state as soon as it's connected, the concept of an edge port is extremely important in Rapid STP and multi-STP. Recall that as part of its improvements over legacy STP, Rapid STP uses a so-called proposal agreement mechanism to rapidly yet safely enable a link between switches if one of the switches has its root port of that link. On ALS1, issue the command debug explanatory events that configure faceted switch to be in VLAN 120. Finally, not shut down the interface and observe the Syslog. Okay, on ALS1, in my case, the interface connected to the computer is gigabit 13. Okay, and use this on ALS1. Configure terminal in exit debug spanning tree events. Okay, configure terminal interface gigabit 13. Okay, set this interface access mode, switch port mode access, and assign to VLAN 20 access VLAN 120. Then now shut down. Okay. Okay, will take some time. Okay, may take a while. Okay, initializing port now is designated. Transmitting the proposal. Okay. Finally, generating TCP trap, TC trap for port 13. Okay, now shut down the port. Shut down. As you can see in the output, Rapid Spanning Tree protocol sees the interface come up, recognizes it as designated port, and starts sending proposals. Now we will add the spanning tree port fast command to the interface. The debug is still running. Not shut down and not shut down again. Okay. Obviously, verify how port fast works. Okay, interface gigabit 1.3, switch port spanning tree port fast. Okay, now enable the interface. Now shut down. Okay, and no proposals. Okay, the port is now designated, and that's it. Very good. Shut down again. Okay, and now enable again. No shut down. Okay, very simple. Obviously, port fast should never be enabled on ports connected to another switches. Doing so could cause a switching loop. On trunk interfaces, configuring the spanning tree port fast command will have no effect. This is a safety precaution. Cisco also provides the way of globally configuring the port fast on all access ports using the spanning tree port fast default global configuration command. With this command configured, each port that operates in the access mode will automatically have port fast enabled. Trunk ports will not be affected. Implement and observe Bpdu words. Port fast causes an interface to go into forwarding state immediately. There is a risk that if two port fast enabled ports are inadvertently or maliciously connected together, they will both come up as forwarding ports, immediately creating a switching loop. The default expect behavior of port fast port that receives a Bpdu is for that port to revert to a normal spanning tree non-edge port. There is the potential that the load of a given switch may be too great to handle the received Bpdu properly, prolonging the loop condition. Bpdu ward adds another layer of protection. Whenever a port protected by Bpdu ward unexpectedly receives a Bpdu, it is immediately put into error disabled state. Any interfaces can be protected with Bpdu ward, but it's typical use in port fast enabled ports. Bpdu ward can be configured globally or on a per interface basis. If the Bpdu ward is configured on the global level using the spanning tree port fast Bpdu ward default command, the Bpdu ward will be automatically enabled on all port fast enabled ports of the switch. If the Bpdu ward is configured on a particular interface using the spanning tree Bpdu ward enable command, it will apply to this port unconditionally, regardless of whether it is a port fast enabled port. For this example, we will configure Bpdu ward on a trunking interface that is a non-root port on ALS2. Configuring Bpdu ward an interface that is intended to be a trunk is not recommended practice. We are doing this just to demonstrate the functionality of the tool. Okay, on ALS2 Fast Ethernet 11. Okay, ALS2 11 is 111 in my case. Configure terminal interface gigabit 11. Okay, spanning tree Bpdu guard enabled. Okay, receive Bpdu on port gigabit 11 with Bpdu guard enabled, disabling the port. Bpdu guard error detected within gigabit 11 in error disabled state. As you can see, the interface is almost immediately error disabled. Okay, revert the configuration. Okay, first of all, shut down the interface and remove the port fast. No spanning tree port fast. Disable Bpdu guard. Spanning tree Bpdu guard disabled, and enable the interface with the no shutdown command. Okay, interface up. Implement and observe Bpdu filter. Neither port fast nor Bpdu guard prevents the switch from sending Bpdus on an interface. If such a behavior is required, Bpdu filter can be used. It can be configured either globally or at the specific interface. If Bpdu filter is configured on the global level using the spanning tree port fast Bpdu filter default global configuration command, the Bpdu filter applies only to port fast enabled ports. When these ports come up, they will send up to 11 Bpdus and then stop sending further Bpdus. If the Bpdu filter configured interface receives a Bpdu at any time, the Bpdu filter and port fast will be deactivated on that port and it will become a normal spanning tree interface. As a result, a globally configured Bpdu filter does not prevent ports from receiving and processing Bpdus. It only attempts to stop sending Bpdus on ports where most probably there is no device attached that would be interested in processing them. Configured an interface Bpdu filter causes the port to stop sending and processing received Bpdus altogether. This can be used, for example, to split the network in two or more independent STP domains, each having its own root bridge and resulting topology. However, because these domains are not longer protected against mutual loops by STP, it is the task of the network administrator to make sure that these two domains are never connected by more than just a single link. To test this feature, we will run a packet capture utility on host A connected to LAS1, configure Bpdu filter on an interface for Ethernet 6 and see that Bpdus stop being transmitted. Logging on host A, run your packet capture utility and filter the output shown only STP packets. In Wireshark, the filter bar should look something like this. LXC okay, simulation LXC SSH management. Yes, Cisco. Okay, on Ethernet 1. Okay, first of all, verify ifconfig. Okay, Ethernet 1. TCP dump interface Ethernet 1. Okay, and sudo, because says you don't have permissions. Okay, use sudo Cisco. Okay, is capturing packets. Control C to stop. Okay, 4 packets captured, 4 packets received by filter. Okay, for example, this is the timestamp, an STP packet for this protocol AF2.1W for rapid spanning tree. Okay, learn and forward. The bridge ID. Okay, look at this. Look at this MAC address. On ALS1, show a spanning tree. Okay, this MAC address. Okay, is this. Okay, this is the this is the MAC address of the switch. That's why it's the bridge ID. Also, you can see the CDP, the Cisco Discovery Protocol version 2. Okay. And more rapid spanning tree packets. You should see a Bpdu being received at your host every 2 seconds. Okay, look at this 0, 2, 4, and so on. Okay, 23, 25, 27, and so on. Okay, that's very good. Every 2 seconds. Now, configure Bpdu filter on ALS1 interface fast Ethernet 6. Okay, is the interface connected to the PC? Okay, that should be configured on gigabit 13 on ALS1. Configure terminal interface gigabit 13 and configure spanning tree Bpdu filter enabled. Okay, but before press enter, capture packets repeating the command. Okay, on DLS1, on ALS1, enter and next. Okay, go to terminal. Okay, for example, 24, 26. CDP and 24 and 26 rapid spanning tree frames every 2 seconds, but no more frames. Okay, only CDP. No more frames for rapid spanning tree. You will have stopped receiving Bpdus. Okay, that is the demonstration. And Control C on the capture. Implement and observe root ward. Root ward helps prevent a root switch or root port takeover. It is configured on the port to be protected. If a port protected by root ward receives a superior Bpdu that would normally cause the port to become a root port, the Bpdu will be discarded and the port will be moved to the root inconsistent state. An STP inconsistent state differs from the error disabled state that the port is not disabled entirely. Instead, it is only put into blocking discarding state and will be put back into its proper role and state once the cause for its inconsistent state disappears. With root ward, a port will be reinstated into its appropriate role and state automatically when it stops receiving superior Bpdus. Bpdu root ward is a protective mechanism in situations when your network and the network of your customer need to form a single STP domain. Yet you want to have the STP root bridge in your network part and you do not want your customer to take over this root switch selection or back up the connectivity in your network through the customer. In these cases, you would put the root ward on ports toward the customer. However, inside your own network, using root ward would actually be harmful. Your network can be considered trustworthy and there is no rogue root switch to protect against. Using root ward in your own network would cause it to be unable to convert on a new workable spanning tree if any of the primary links failed. And it would also prevent your network from converging to a secondary root switch if the primary root switch failed entirely. To illustrate the behavior of root ward, we will configure it on a designated ports on DLS1 for VLAN 100. DLS1 is the root bridge for VLAN 100, so all trunk ports are designated. Okay, on DLS1, show a spanning tree root. Show spanning tree root. Okay. For VLAN 100, DLS1 is the primary root. Okay, but show a spanning tree VLAN 100. Okay, all ports are designated for because this bridge is the root. Okay, this bridge is the root for VLAN 100 and all ports are designated ports. Okay, and configure root ward DLS1 on interface Ethernet 7. You may immediately see errors with another VLAN like 666. Ignore this and we are focusing on VLAN 100. Okay, on DLS1 on Ethernet 7, in my case is gigabit 01. Okay, gigabit 01 configure root ward, configure terminal interface gigabit 01, spanning tree ward root. Okay, this is the debug activated. Okay, exit. Then go to LAS1 and configure it to be the root for VLAN 100 using the priority 16,384. Okay, ALS1 enter. spanning tree VLAN 100 priority 16,384. Okay, the debug. Back to DLS1. And verify the gigabit 01 and show spanning tree interface gigabit 01 and include the keyword VLAN 0100. Okay, on DLS1, the designated BKN broken and root inconsistent message. This output has two indicators of the issue. First, BKN is short for broken, and root INC represents the root inconsistent message. A list of all STP inconsistent ports, including the reason for inconsistency, can also be requested with the command show spanning tree inconsistent ports on DLS1. Show spanning tree inconsistent ports. Inconsistent ports. Okay, gigabit 01 for VLAN 100 root inconsistent. And to clear this, go back to ALS1 and issue the command no spanning tree VLAN 100 priority 6,384. Once you do this, you will see the following syslog message on DLS1 and the interface will become consistent again. Okay, go back to ALS1. The interface okay, remove the previous configurate command. Now spanning tree VLAN 100 priority 16,384. Okay. This will set the priority to the default value. Okay. Go back to DLS1 and verify. Repeat the previous command, show spanning tree interface gigabit 01 and include VLAN 0100. Look at the debug, dispute resolved. Okay, enter. Now is forwarding, is consistent. Okay, the designated port. Remove root word from Facetnet 7 on DLS1. In my case, gigabit 01. Configure terminal gigabit 01 and remove the no spanning tree word root. Then exit. Implement and observe loop words. The last tool we will demonstrate is loop word. Its job is to prevent root and alternate ports from becoming designated ports if Bpdus suddenly cease to be received of them. In a normal STP network, all ports receive process Bpdus, even blocking discarding ports. This is how they know that the device at the other end of the link is alive and still superior to them. If a blocked port stops receiving the Bpdus, it can only assume that the device on the other side is no longer there and they are now superior, and should be in forwarding state for the given segment. An example of when it could occur is the instance where the receiver fiber in an optical cable becomes disconnected, cut, or connected to a different port or device than the corresponding transmission fiber, in a sense creating a unidirectional link. This could cause permanent switching loops in the network, so loopguard helps to prevent them. For this example, we will configure loopguard on an alternate port on ALS2, and then stop sending out Bpdus from the corresponding designated port of the other end of the link, and observe the behavior. On ALS2, show spanning tree below 100, show spanning tree below 100, show not clear. Look at this, gigabit 02 is the alternating port and blocking state. Also gigabit 11 and gigabit 12 alternating states, alternating role, blocking state. But for VLAN 100, the root ID is the DLS1, and from ALS2 to reach DLS1, the root primary, gigabit 01 is used. Here ALS2 tells us that its path to the root is using fast Ethernet 07, and in my case gigabit 01 and DLS2 switch, while fast Ethernet 11 and 12 towards ALS1, in my case gigabit 11 and gigabit 12 are alternate ports because the total path cost for more through ALS1 it is 38, 19 plus 19. In my case is 8, 4 plus 4, down through DLS2 31, 19 plus 12. In my case 5, in my case 01, 1 plus 4, in my case 5, 1 plus 4. Configure loopguard on ALS2 fast Ethernet 11 interface. Configure terminal interface gigabit 11. This spanning tree word loop. Exit. In my case, it's not fast Ethernet 11, it's gigabit 11 on ALS2. Interface facing ALS1. Modify the interface fast Ethernet 11, in my case gigabit 11 on ALS1, to stop sending Bpdus. ALS1 interface gigabit 11, in my case spanning tree Bpdu filter enabled. then exit. Okay, look at the debug messages. Go to LAS2. This is the Syslog message. Loop word blocking port gigabit 11 on VLAN 100. Also on VLAN 99. On LAS2 verify, show spanning tree inconsistent ports. Okay, it's show spanning tree, not clear. Okay, gigabit 11 for VLAN 100. Fix this by reversing the configuration at ALS1 and verify ALS2. Okay, go back to ALS1 on gigabit 11 facing gigabit ALS2. Remove the previous command spanning tree Bpdu filter enable and change to disable. Okay, go back to ALS2. Loop word on blocking port gigabit 11. Okay, verify the inconsistent ports again and no inconsistent ports. Okay, end of lab. Use the TCL script created lab 1 to clear and reload all of your switches before the next lab. Thank you very much.